Hello class, and welcome to week 2 of Information System Security, CMGT431. This week we're going to look at types of applications, common threats, SDLC security, and business continuity planning. Again, all quoted material is from the official ISC Squared Common Body of Knowledge by Stephen Hernandez. Types of applications recognized by the common body of knowledge are agents, applets, client-server, distributed, and web applications. Agents are part of larger applications or solutions, and the agents are pieces of software that run on the local device and communicate back with a primary application or a larger application on something like a server. Examples include antivirus. With an antivirus solution, you can have a centralized management application that communicates out to the devices, telling them when to update their antivirus. The agents can communicate back, stating that the antivirus has detected something on the device. So the agent allows seamless communication back to the centralized solution. Patch management works very much the same way, and configuration management, allowing configuration of systems, and their agents can also do what's called host checking to determine whether or not a device is up to date on its patches and whether it's configured properly before it's allowed onto the network. So here's just a graphic on how agents might work. You have a patch management server. The agent on the laptop PC is sending in the patch status to the patch server, and the patch server is sending out patch directives to a desktop PC. The agents also run on servers in the data center. Agents are not limited to end user devices. An applet also runs as part of a larger program. It's particularly found in web applications or applications that run in web browsers. Examples include flash players, content viewers, and information delivery, things that pop up a window and deliver information to the user, or an applet might collect information from the user to send back to the server. So here's an example of how an applet might work. An applet is usually a Java application or script within an HTML document. The browser reads the document, interprets it, finds that based on a user's action that a JavaScript must load or a Java application must load, and the loader goes out to the .class files location, pulls in the applet, and executes it. Here's an example of what an applet might look like. In this case, the applets is lights.class, and when this is executed, flashing lights come up. If you want more information on how applets work and how they're integrated into HTML, go to the link at the bottom of the slide. Client-server applications have been around for quite some time. They allowed software components to run on the local device as well as the server. This took some of the network traffic off the enterprise network, because a lot of processing, a lot of the things that the user needed to do were done on the client. You can go so far as to define client-server as just providing a user interface to the user. However, in most cases, client-server consisted of a client application that ran on the user device that may do some processing of the data before it goes to the server, processing of the data when it comes back from the server. So it can run anywhere from just being a dumb terminal application to doing some of the processing and taking some of the processing load off of the server. So here's an example of what that might look like. Distributed applications distribute data and applications across different servers in a data center, or they could be in different data centers in different geographical locations. They usually consist of multi-tier architecture, and the data is located where it is best serviced, or where it can best service the users. This does not mean that a user might not make a request, and the request might go out to servers in multiple countries to display a single screen of information. There are two major types of distributed, 2-tier and 3-tier. A 2-tier has a user interface front end and a database back end. The database, remember, can be multiple databases. The 3-tier uses middleware. So between the end user device and the server, there is another server that runs what's called middleware. The middleware actually determines where the data might be kept that the user needs to access. It'll implement any business rules. It'll take that information, aggregate it, and send it back to the user. This is an example of what a distributed system might look like. Notice in this case, the government database you have a government records server, and you have a separate map database. However, the user has no idea that the information resides on two databases. If the user requests government records information and an associated map, the map and the records information are simply sent to the user workstation, and it appears as if they came from a single source. Web applications run on web browsers, and most organizations are moving in this direction because of the lower cost of ownership, better network performance, thinner clients. You don't have to put a lot of applications on the device and user devices like you do for client server applications. And because they run in browsers, almost every end user device is supported. The next slide we're going to look at is showing how a web application typically works. And this is from the site on the slide. So this graphic is important because from this graphic, for your assignments over this week and next week and subsequent weeks, you can actually use this to help to visualize where you might place controls. So in this particular example, the user submits a shopping cart order on the website. The web server receives the information from the user and sends it to the web application server. Notice that the web application server is not accessible by the user. Instead, the user only accesses the web server. The web server then accesses the web application server, and the web application server accesses the database servers. This is a typical implementation, and usually the web servers in a case like this would reside in a demilitarized zone where the user can access the web servers but is blocked from getting any further than the web servers. When we talk about web applications, we also want to talk about the vulnerabilities that are specific to web applications. Your book provides vulnerabilities in the OWASP top 10, but the OWASP top 10 in the material is actually outdated. The OWASP top 10 from 2013 is what we're going to look at in this slide. And these top 10 vulnerabilities are listed in order of how often they occur in an enterprise. The first one is an injection attack. An injection attack occurs because an application or a developer did not check to see whether or not the information coming into a field, an input field, is what was expected. So this is called input validation. So when input validation is not done, or it's done incorrectly, injection attacks can occur. So what happens is an attacker will actually add code to the end of a field entry that, when sent back to the database server, performs a specific function, like providing a listing of users and credit card number, or customers and credit card numbers. Next one is broken authentication and session management. Poor authentication or session structures expose passwords, keys, or tokens. So it's important to understand how information is protected. Is it encrypted, and is this sensitive information encrypted in some way? Is it shared across processes? If it is shared across processes, is every process required to authenticate before it can use those things? These are all information. This is all information that needs to be addressed when developing a web application. Cross-site scripting is when an application takes untrusted data and sends it to a web browser without proper validation. Again, lack of input validation. When you have lack of input validation in cross-site scripting, it allows an attacker to execute script on a user session that is unexpected and usually malicious. Again, once again, and I can't say this enough, this is preventable by always checking the data you expect, either whether it's pulled from a database server or entered by a user. Insecure direct object reference. Whenever a process in a web application can access a resource, it needs to be authenticated, and it needs to be authorized to access that resource. As I mentioned before, even with shared resources, you should not be able to share objects across processes unless each process is forced to authenticate and is authorized to access those processes. Security misconfiguration. Security settings in web browsers or in web servers must be configured in such a way as to secure any sensitive information. In addition to that, all software should be kept up to date. Vulnerabilities are found all the time in web server software. Those patches must be applied. The next one is sensitive data exposure. Sensitive data is any data that's classified as confidential or restricted or top secret, and that data needs extra protection. So if it's moving from one device to another, if it's moving between a browser and another application, how is it protected? So this goes to encryption, and it also goes to what we talked about 2 or 3 times so far, and that is making sure that any process that accesses data is supposed to do it, that it's specifically checked to make sure that it's allowed to have access to the data. The next is missing level access control. So most web apps verify function level access rights. In other words, authorization. What is the user allowed to do before making that functionality visible in the user interface? However, applications need to perform the same access control checks on the server when each function is accessed. So in other words, just because you present the functions to the user on the user interface does not mean that the server shouldn't check again to make sure that those functions, first, are allowed to be run, and second, they're allowed to access the data that they're attempting to access. If requests are not verified, attackers will be able to forge requests in order to access functionality without proper authorization. And this brings us to cross-site request forgery. A cross-site request forgery attack forces a logged-on victim's browser to send a forged HTTP request. It uses the victim's session cookie, a valid session cookie, and any other automatically included authentication information to a vulnerable web application. This happens a lot when users fail to log out of sites like banking sites and go on about their business browsing other sites. This allows the attacker to force the victim's browser to generate requests the vulnerable application thinks are legitimate requests from the victim. In other words, as far as the server is concerned, the user is actually the authorized user is trying to access the sensitive information, when in fact the user's login information, the session cookies, the passwords are all being used by the attacker because the user probably had that session still active when malicious code was initiated on the workstation. Next is using components with known vulnerabilities. Components such as libraries, frameworks, and other software modules almost always run with full privileges, which means they can do anything they want. They can modify information, they can access any information. So if a vulnerable component is exploited, it can take over a server or result in serious data loss. So applications using components with known vulnerabilities undermine application defenses and enable a range of possible attacks and impacts. And the final one is unvalidated redirects and forwards. Redirection attacks are pretty common today. Web applications can redirect and forward users to other pages on websites and use untrusted data to determine the destination pages. So the attackers can redirect victims to phishing or malware sites or use forwards to access unauthorized pages. Another thing that can be done, which was presented at Usenix, as a Usenix symposium this year, was the ability to redirect users who are using password management software so that passwords can be stolen with the because the users have the autofill function turned on the password manager. And those types of redirects, the user doesn't even know they've been redirected. It simply flashes momentarily on the screen before it goes to the page that they're expecting. So for a complete list of an analysis of everything we've talked about here, you can go to the link provided on the screen. This is probably the best resource for assessing the top vulnerabilities in web applications. OWASP also provides a really good list of all possible threats and threat categories. So again, this is a valuable site. OWASP.org is a valuable site when doing threat assessments and risk assessments. Next, we're going to look at common threats. Common software threats include buffer overflows, malicious software, input attacks, object reuse, mobile code, social engineering, and backdoors. Buffer overflow, as defined by OWASP.org, is caused by a developer not restricting input to conform to input variable. So again, it's caused by lack of input validation. If you expect a 10-character input, don't allow a 30-character input. Only allow the 10 in your interface. Because if you allow a 30, those extra 20 characters are going to spill over. They're going to exceed the buffer, and they can be used to inject malicious code into a process or into a stack. So again, input validation. Not only do you check to see if you're expecting characters, you're getting characters, numbers, you're getting numbers, but you also need to check and make sure that the length of the field is what you've allocated in the application for that field. And that's done at the time that the user inputs the data in the user interface. Malicious software. We have various kinds. First are viruses, which are the first ones that we encountered. And these definitions are straight out of the common body of knowledge. So a virus is a set of coded instructions designed to attach to an object capable of containing the material without knowledgeable user intervention. This differs from a worm, which does not require any action to reproduce and spread. A worm will actually, once installed on an end user device or on a server, will go out and look for opportunities to move copies of itself to other devices. Viruses can't do that. Trojans pretend to do one thing while performing another unwanted action. So you may bring down an application that you download it, some free app that performs a specific function for you, but in the background, it's actually doing other things that you probably would rather it didn't. Remote access Trojans, like Blackshades, Black Orifice, NetBus, Bionet, and Sub7, allow remote control of a system once they're installed. Rats are pretty common Trojans, and they once they're on your system, you pretty much have lost control of it. The master computer of the attacker will be sending commands down to the system. Your system will be reporting back, and it's really your system can be used, whether it's a server and user device, can be used as a launching platform for attacks against other devices. It can be used as a denial of service bot. It can be used for just about anything at this point. And that brings us to distributed denial of service zombies, a specialized form of rat or bot used to launch denial of service attacks from multiple devices at once. Logic bombs. Logic bombs are designed to run in the background, just checking continuously to see when a specific set of conditions occurs. When that specific set of conditions arises, then the logic bomb activates its payload and performs the task the attacker needs it to perform. So one current example of this is the Citadel Trojan. Current in the news recently, the Citadel Trojan, which is a keylogger, waits until you launch one of two password managers, and then it watches or captures the keystrokes as the user types in the master password for the password manager. Other than that, it doesn't run. It just sits dormant, again, waiting for the user to launch the login screen for the password manager. Spyware and adware. Sometimes they're malicious, sometimes they're benign, but in all cases, we really prefer them not to be on our systems. They can collect data about the user's behavior, They can provide advertisements based on users' activity, users' behavior. They can also collect information that is private and send it back to attackers for use in privacy or use in identity theft, etc. Pranks are common, where someone will send out a message saying, "Hey, look, there's this virus going around, or this worm going around, and you need to do this to your system so that you can protect yourself." Or a prank can also be something that I pulled on a friend's father, and he was not pleased by it a long time ago, where we put on a virus, and it was a prank virus. Didn't do anything except pop up a message that's saying it was cleaning his drive, and the sound of a washing machine came on. So these are examples of pranks. Whenever a user receives a message, or you receive a message stating that you need to do something quickly because there's a virus going around that does A and you need to do B, you need to check and make sure that it's not a prank. Almost all of the antivirus or anti-malware vendors offer information about these types of messages, and they're a good place to check again before you do anything. And botnets are a network of automated systems or processes performing a specific function. Normally, a botnet is controlled by a malicious group. A lot of organized crime organizations use botnets, and they sell their services to people who want to collect specific types of information, who want to create denial of service attacks against targeted organizations, or any other activity that requires a large number of devices participating in order for it to be cost effective for the attacker. Input attacks. They're caused by developers not validating input. Again, inspect what you expect. There are so many reasons, and so many threats that take advantage of lack of input validation, that it should be the first thing the developer does the minute that he or she adds an input field. It should be surrounded by validation code. Object reuse. We talked about this a little bit in the OWASP Top 10. It's when an object or resource is shared by different processes, and nothing should be shared or passed from one process to another. No area of memory should be shared unless all relevant processes, or all processes accessing those resources, are authenticated and authorized. Mobile code. Mobile code is not code that runs on mobile devices. Rather, it's code that moves around based on what a user is doing. In our examples, we have ActiveX, Java, JavaScript, Flash, and Shockwave, and any downloaded software. In today's threat landscape, these are some of the most common ways that users get infected. So, one of the best, you can deny execution of any downloaded software or website content, or you can remove administrative access or administrative rights from all your users. Even IT personnel should not be browsing the web with administrative rights. If you turn that off, that puts a big locked door, not impossible to circumvent, but very difficult to circumvent for an attacker who's trying to get malicious code onto a device. Social engineering is manipulating user behavior to achieve an intermediate or final attack objective. It can be done with a phone call. It can be done by standing in front of somebody at their desk. It can be done with email, but it always relies on users wanting to do the right thing or being afraid to do or afraid not to comply for some reason, and usually in the absence of awareness of existing threats. And absence of awareness of existing threats is usually caused by a lack of training by the organization. A backdoor is something intentionally added to software during development or to security configurations during system implementation to allow the attacker to bypass security controls. This used to be done a lot in the past when we had when I programmed on an AS400, IBM AS400, a mid-range system, where we'd put in backdoors so that we could easily bypass some of the security to get in, but we don't do this anymore. Backdoors are something that should never be allowed. And during code review, when another developer is reviewing the primary developer's code, should be something that is looked for. Other threats include human threats, malicious outsiders, disgruntled employees, saboteurs, spies, both political spies and corporate spies, loss of key personnel, and human error. Natural threats include fire, flood, weather, earthquake. Technical threats include hardware failure, software failure, unauthorized use, and capture of data in motion, at rest, or being processed. Physical threats are something that are often overlooked. And a physical threat is the potential for an attacker to come through locked doors, to get access to physical access to servers and workstations. Physical access to servers and workstations or to network devices is very, very bad, because in many, many cases, physical access means game over. There are defenses that you can implement for physical security, and a detailed discussion of physical security is included in the chapter at the link shown on the screen. Now let's look at the SDLC, or System/Software Development Lifecycle. The SDLC can take on different phases depending on whose version of the SDLC you're looking at. The phases I have here are out of the Common Body of Knowledge book that I quoted at the beginning of the lecture. So phase 1, project initiation and planning. In phase 1, we conclude a preliminary risk assessment. In this way, we can look at all the risk associated with the solution that we're looking at and put together security requirements. Phase 2 is functional requirements definition. Functional requirements are those requirements that the business needs to be able to achieve the outcomes it expects from the solution. Again, we take the risk assessment information from phase 1 and use it in phase 2 to define security requirements around the functional requirements. Phase 3, system design specifications. We design security features to comply with the security requirements. So notice, we're not just adding on security, we're actually including security in the design of the solution. Phase 4, development and implementation. Here we ensure expected security outcomes are included in the use cases for testing. So when we create a test environment, when we create a test plan, we create use cases that say, okay, the AP clerk is going to perform this function, and to do that, they have to go through these steps. That's a use case. So we have to make sure that the security outcomes for that use case are actually met, making sure that the AP clerk in our example can only access the data that he is supposed to be able to access,
and is only able to do with that data what we expect him to be able to do with that data. Phase 5 includes documentation and common program controls. This is where we start testing. So we're testing authorization. Are we properly controlling what a user can do once they have access to the system? Components, hardware, software, files, databases, reports, and users. Do security requirements address all the different components of the system, including the pathways over which data is going to travel, all interfaces between the system and other systems, restart and recovery procedures, part of business continuity, logs, part of ensuring that we can either recreate a security incident or that we can, real time with a security information and event management system, identify anomalous behavior, timestamps, internal checks, input validation. And where we talked about input validation, when we talked about the OWASP top 10, it's very important that when we test a system, that we test to make sure that we can only enter information into fields that are expected to be entered, nothing else. And valid and legal address references. Now, a lot of these things during software system development in phase 5 are checked during what some people call a buddy check. And that is where another programmer takes the work of the primary developer and checks it and ensures that all the things that are expected to be in there are there, and there's nothing extra there like backdoors and other types of things, logic bombs, whatever. So having another set of eyes look at the code helps to ensure that, one, that you're meeting all of the internal control requirements, and two, nothing special is added. Phase 6, testing and evaluation control. So now we use the use cases created in phase 4, and we test to make sure that all security requirements are met. This also includes evaluation and certification. And according to the book, this means the security stance of the software or system against a predetermined set of security standards or policies is compliant. Phase 7 is transition to production or implementation, and this includes training users to ensure awareness of potential security risk. It includes training users on the processes and procedures, the step-by-step procedures that have been built in order to comply with policy. Phase 8 is operations and maintenance support. This includes monitoring of the system, incident response in case something fails or in case there's a breach or an attempted breach, business continuity in case a piece of the hardware or the software fails, being able to continue the business processes associated with the system. Phase 9, revisions and system replacement. In this particular one, we're talking about making changes to an existing system first. That's the first thing we talk about here. And to do that, we should be running it through a change management process. In a change management process, several different groups or the stakeholders need to be able to review a change to make sure they're okay with it. In addition, a change plan or a change request should also include a backup plan in case the change that's made breaks the system. Change management fundamentally is about making changes to a system without breaking anything. When we make a change, we also have to do another risk assessment to make sure that any changes that we made do not increase risk above an acceptable level. And this is why security should be involved in the change management process. System replacement is about making sure that when we replace this system eventually, and all systems are eventually replaced, that we sanitize the media, we erase drives completely, not just delete files, because that does not make the data inaccessible, but to use media sanitation techniques to make the data on drives and any other media, tapes, whatever, inaccessible. Business continuity and disaster recovery. purpose of business continuity planning is to ensure continued business operation when the supporting people or technology are not available to support business processes, whether critical or otherwise. Although most business continuity planning revolves around critical business processes, those processes that can't be done very long before the company experiences a catastrophic or traumatic event, which could result in the company never recovering. A disaster and disaster recovery planning is a subset of business continuity and business continuity planning. A disaster is a natural or man-made event that requires considerable and coordinated effort to continue business operation. So the difference between a business continuity event and a disaster. In a business continuity event, just a basic event, you might lose a server or a server drive. So temporarily, you can send in an engineer, the engineer can fix it, and you're back up and running. With a disaster, you might lose the entire data center. When that happens, you need a whole team of people to, one, come up with workarounds or to implement the workarounds you've already documented to ensure your critical business processes continue, and you need a team of people to recover the technology so that you can restore business critical processes to their states prior to the disaster. So a disaster is a massive hit on an organization's ability to operate. So what are the outcomes of a BCP? Well, the business impact of each incident is minimized. And here is a formula that should look reasonably familiar. It's one that was in the common body of knowledge. But it's a probability of harm times the magnitude of harm equals the cost of prevention. In other words, if we take the probability that an incident will occur, you've got threats and vulnerabilities, times the business impact or multitude of harm, we get a value. That value should be what we use as a bar when determining how to build a business continuity plan for a system. So if the cost of a business continuity plan is more than the probability times magnitude of harm annualized, remember we annualize this information, then we probably should look for another business continuity plan for that system. What you want to do is not spend more on business continuity planning for a system annually than the projected annual cost of a business continuity event related to that system. The next bullet is very important. It's very important if you decide to go take the CISSP exam. The most important element of a business continuity plan is human safety. So human safety must be addressed. Corporate liability due to lack of due diligence is mitigated because if you can demonstrate that you have an up-to-date, practiced, and documented business continuity plan, then the public is less likely, or your customers are less likely, your shareholders are less likely to go somewhere else because they know that you practiced what's reasonable and appropriate to plan for and mitigate a business continuity event. This also applies to the organization's public image. It's protected by a fast professional response. Incident response is incredibly important. How an organization responds to an incident not only determines how fast business critical processes are recovered, but it also will determine how that organization is viewed by outsiders. So the benefits of BCP are reduced risk, process improvements, improved organizational maturity, improved available and reliability, and market advantage. Any organization that has a good, solid, practiced, and I can't say this enough, practiced business continuity plan can demonstrate this to potential customers and shareholders and show that it is at a lower risk than a supplier of product, another supplier of product that has not planned ahead. So let's take, for example, that an organization is in a critical link in a supply chain for a manufacturing company. That manufacturing company, as part of its business continuity planning, wants to ensure that all of the links in the supply chain also have taken into account business continuity planning. If it finds that an organization in its supply chain has not practiced due diligence, is not testing its business continuity plans, is really hasn't spent a lot of time with business continuity planning, then that is a huge risk for that manufacturing organization, and they're probably going to replace that link in the supply chain with somebody who does get it. Business continuity planning is an ongoing process, and this link shown under the title is from NIST publication SP 800-12. And the process includes identifying business critical functions. Notice we're not saying identify business critical systems. We're saying that the first step is to identify business critical functions. Because remember, the purpose of a business continuity plan is not to keep a server up and running. It is to keep business critical functions or processes running. Number two, identify the resources that support the critical functions. It is at this point that we look at servers, end user devices, routers, switches, and anything else that is required to support the business critical function that we're looking at. This also includes identifying single points of failure. So if we have one server that is providing web services for our customers, and that server fails, that's a single point of failure. We can remediate that by using multiple 2 or 3 web servers, and we load balance the incoming traffic so that if one fails, we still can continue operating while we replace the other server. That's an example of eliminating a single point of failure. So for each critical business process, we anticipate potential contingencies or disasters. In other words, we look at the threats, the potential threats, or the probable threats that could cause a business continuity event. We select contingency planning strategies. This starts with looking at the maximum period of tolerable downtime. How long can a system be down before it causes irreparable damage to a business? And when we look at that, we have to look at 2 different things. We have to look at the recovery time objective and the recovery point objective. When we recover a system, there is still some cycle time that is required to bring the business processes supported by that system up to the point where they were at the point of failure or when the business continuity event occurred. So the recovery time plus that cycle time to get back to the point of failure is your maximum period of tolerable downtime. It's not just the downtime of the server or the switch. It's the downtime of replacing the switch, replacing the server, rebuilding the server, plus the cycle time of getting back to point of failure. So the recovery point objective is where we want to be when we've recovered the system. That will determine how much time it's going to take to cycle up to where we were at the point of failure. So these 3 things altogether need to be considered by the business continuity team and all stakeholders to determine how fast a system has to be brought back up online, how backups have to be done so that we can get to a specific recovery point objective. Number 5 is implement the contingency strategies. In other words, do your backups, have spare equipment if that's what it takes, get a hot site or cold site contract set up. And then 6 is to test and revise your strategy. So your business continuity plan, your disaster recovery plan must be tested. There are different ways to test. There are tabletop tests where everybody sits in a room and walks through a disaster and determine, or a business continuity event, and tries to find holes in the plan. That is probably something that can be done every single time there's a change made, or annually for systems that support business critical processes. The more time-consuming and costly test is probably usually done annually, and that's where you actually go to a hot site. You actually go to a co-location data center and test bringing a system up and making sure that your business continuity plan does get the system up within the recovery time objective and restores the system to the recovery point objective so that everything comes together in less than the maximum period of tolerable downtime. If it doesn't, you revise the strategy and try again. So the components of a BCP, and this is from our text, so included in a business continuity plan, we have recovery team members. Now there can be multiple recovery teams depending on what a section of the business continuity plan is addressing. Emergency response, what to do when an event occurs. Damage assessment and salvage, what do we do as far as who's responsible for damage assessments, who gets notified, which is the next bullet. What do we do with damaged equipment? Personnel safety. What are the steps we take to ensure human safety? Communications. How do we communicate not only with employees and management, but also with our customers and shareholders, letting them know what happened and what we're doing to fix the problem. Public utilities and infrastructure. We should know all the points of contact for all our public utilities and other infrastructure organizations so that we can call them and coordinate with them in case something fails or in case we have to shut down a utility because of some damage to our facility. Logistics and supplies. If we're going to replace a server, how fast can we get it? Have we made arrangements with our server vendor to be able to get something in 24 hours? How about a memory board? How about drives? Have we made arrangements with our storage vendor so that we can replace either the logic of the storage device or specific drives within the device? And this should all be documented and in the logistics and supplies. The other thing that goes in logistics and supplies are those things that are needed for us to maintain business operation by working around the technical failures. In many cases, we can continue business critical processes by using paper and pen. I know that sounds weird today, but sometimes that's what's necessary to keep the business running. Fire protection. What have we done to prevent or to control fires in our data center? Business resumption planning. What happened? How do we get our customers back on board? How do we get our systems back up and running? Again, this goes back to making sure that we have colo sites, making sure that we have the right teams and documentation in place to get our technology up and running. That goes along with restoration and recovery. Something very important here is build documentation for every single technology component supporting a critical business critical process. We need to not guess on how to build a server. We need to be able to put a server together, have the step-by-step instructions for how to do that. If we use virtual servers, this becomes pretty simple. As long as all of our virtual server images are up to date, all we have to do really is grab an image and bring it up, and they should instantiate it on another server, a new server, an existing server that's a blade server, for example, that's sitting there just waiting for some critical piece of technology to go down. It's not like in the old days where we had to have a discrete server sitting around, or had to order a discrete server and then try to build it from scratch. Today, with virtual servers, it's pretty simple to get critical systems back up and running quickly, simply by taking and instantiating a virtual image on a spare blade server, spare host server. So that's the end of the week 2 lecture. Again, this is just a supplement to the reading. It's not a replacement. I do encourage you to ask questions in the classroom. It's very important, again, that you get these points from this week before moving on to week 3.